Okay.
I have to leave today regularly.
Yeah, fine.
It's 1:30.
1:30, we are not going to go till there, though.
No, 1:30, well after it at 1:30.
No, but we'll end by 1.
No, I have to go home.
Oh, I see. Oh, okay. Yeah. Okay. Cool. So today we're going to continue on this sort of road on hardness versus randomness. So I'm going to call it hardness versus randomness 2, but technically, because this is going to be a build up towards a result that we will mention today, but then we'll slowly build towards the proof. But the first sort of thing that we need to do is like finish up the proof of the Nisan-Wigderson theorem that we mentioned last time. So let me recall all the things that we need so that we can proceed with the theorem statement. So just want to recall that no, we had two different notions that we were talking about. One was this notion of something being pseudorandom, and the other was a notion of something being next bit unpredictable. Okay, and both of these things usually it's defined in terms of two parameters. Like there is a size parameter and there is how much you're willing to tolerate, the error tolerance. Okay, and this is like saying that something is t comma epsilon pseudorandom if for all circuit C of size at most t, you have that you can't really distinguish the random variable x from the uniform distribution with advantage more than epsilon. Okay, so that's what pseudorandom means. And next bit unpredictability says that for every I you can choose in the locations, there is no small circuit, there is no size t circuit that happens to guess the ith bit given the prefix with non-trivial advantage. Okay, and the advantage, I want this to hold for all possible circuit C and any possible I. Like none of the bits must be predictable given the prefix. Okay, so this was the two notions we were looking at last time, and one of the things that we showed last time was that the other direction was sort of very easy. That if something was pseudorandom, of course it was next bit unpredictable. But the surprising thing was that if you just know this potential weakers like property, which is next bit unpredictability, that is sufficient to get pseudorandomness as long as you're willing to absorb one extra factor of n. So the hybrid argument incurs a factor of n in the error that you have to tolerate. But in most cases, this epsilon is something that we can tailor to whatever we want. So usually this absorbing this factor of n is not a big deal. So you should mentally just tell yourself that next bit unpredictability is basically the same as pseudorandomness. Okay. And then we came up with this notion of something called epsilon hard. Let me quantify this to sort of say epsilon hard to guess. Okay, because we'll be coming up with various other notions of hardness, and sooner or later we'll have to come up with different names. So what does a function being epsilon hard to guess mean? This is a statement again, it's like saying that no circuit should be able to do significantly better than random guessing. Okay, if you were to just given an input x, if you just guess randomly, like the value 0 or 1, well, you're going to be right with probability half. And you want to say there is nothing really spectacular you can do besides more. You can't really do anything given a small circuit. If all you have to do is using a small circuit, well, you might get a little better than half. It might become a half plus epsilon or a half minus epsilon, but that's okay. Like you can't really get advantage better than epsilon here. So that's what hard to guess meant. And the reason we were looking at this hard to guess was because there was a natural way in which we could use, if someone gave us a function that was hard to guess in this regard, you could use that to construct a pseudorandom generator which stretches maybe by 1 bit or something, which would just replace the last bit by the hard to guess function on the previous bits. But of course, that was not it was not a great generator. So then we used this idea of using almost disjoint sets to build a larger thing. And that led us to this notion of what we call combinatorial designs. What is a combinatorial design? It's a large collection of subsets from a certain universe, each of the same size, such that the pairwise intersections are very small. There's a whole bunch of parameters with respect to this, and that's what shows up in this parenthesized expression. You don't really need to care about it. Basically, tell yourself that you are expecting a lot of sets in a reasonably small universe where the intersection size is substantially smaller than the size of the sets. So you should really be thinking of the regime where, like I mentioned last time, that you should probably be thinking of A, or maybe let's say K is some number. That's usually the part that you anchor every other thing based on. And you want to think of L as being something like, I don't know, 100K. Okay. And think of A as something like K over 100. And think of N as something that is exponential in K, or exponential in all of these parameters, because they're all within constant factors of each other. Okay. So that's the rough regime of parameters you should have in mind. Okay. You're asking for a lot of steps in some universe where pairwise intersection does one. Okay. And something that we mentioned last time was the fact that you can construct these designs rather efficiently. Okay, so this was the general thing that we'll be using in the Nisan-Wigderson proof. We gave a sketch of it last time based on codes of a certain property and so on. And roughly what is it saying? That it says that, okay, let's say you want a certain set size K and you have a certain intersection size that you want to get. Now, obviously, I want A to be way smaller than K. But this thing says that as long as even K, like A is like K by 2 or less, this is okay. Okay, so as long as you're dealing with some intersection size which is some A and the following property holds, then it says you can always work within a universe of size K squared over 2A and build exponentially many sets. Okay, so that's what this theorem says. It says that given a K and A, I will give you exponentially many sets in a relatively small universe. Okay, that's how you should interpret the existence thing here. And so once we have these designs, there was this notion of building this Nisan-Wigderson generator. So the generator is defined based on a function. Someone gives you a function f, which is a k-array function. It's something that works on k bits. And based on this function and a certain design, S1 through Sn, that is an NLKA design, you can define this generator, which I'll call NW subscript of f, which is as follows. The generator now has a seed length, which is L, which was the universe size of the design. And how is the generator defined? Well, when I give it a seed, which is y1 through yl, what does it do? It basically takes y1 through yl and looks at the window defined by s1. So this is what I'm referring to as y whatever, restricted to s1. That is some k bits. Evaluate f on that. That's the first bit of the output of the generator. And now you do the same thing for S2, you do the same thing for S3, etc., etc. And these are the n bits that you return. Okay, that was the generator. And the lemma that we are now going to prove is the following. I'm going to state it in the contrapositive direction. Because right now I've made no assumption about the hardness of f or anything. The above definition just works for any f. Okay. So what I'm going to now show is that suppose there is some circuit C that sort of asserts that this thing is actually not next bit unpredictable. That is, it manages to predict the next bit at some height. Okay. I then want to say that, given such a circuit C, I will be able to build a different circuit D that actually guesses the function with advantage at least epsilon. Okay. So this is what we are going to try and show. So basically fix any epsilon and any s that you want. And given such a circuit C that predicts maybe the ith bit for any choice of I will be able to build a different circuit D whose size is now going to depend on S and many of the parameters of the design. Okay, which we'll figure out. I mean, there's no point writing it down. We'll just use the proof to sort of say, what does the proof give?
So this is bit epsilon and right?
Yeah, this is next bit predictable. It's predictable. Yeah.
For a while I was lost.
Yeah.
But then, okay, so and that epsilon and this epsilon,
they are the same. So if you want to replace this by saying that if the output is not pseudorandom, then there is a way of guessing. You will incur a factor of n. In the epsilon will become epsilon by n. It's because next bit predictability and pseudorandomness there is a small gap. This is also why you need that epsilon to go down. Okay, but this lemma, as stated, is probably one of the cleanest things to. Okay, and this is what. So the first thing that we are going to do is try and prove this. So let's see what are we given, and let's see what do we want to get. So what are we given? We are given some circuit C of size S And whenever you have a next bit predictor, you also need to say what I are you predicting? Like what is the length of your prefix and which bit are you predicting? That predicts the ith bit given the prefix. Okay, so let's be formal about what this means. So what is the circuit given? Okay, so the circuit C, the input to the circuit is the following. I am given f of y given s1, blah, 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 till f of y given si. That's what is given. So y was chosen uniformly at random. And these were now, therefore, now some bits, depending on what y was. And I give you these I minus 1 bits. And the goal is to then predict whatever, this f of y restricted to si. Okay, that's what we want to do. Sorry, this is what is given. Somehow this circuit happens to agree with this with probability at least half plus epsilon. Okay, so that's the hypothesis. From this, I want to somehow build a way in which I can compute f. So want to construct D, want to build D, which is now going to take Z1 through Zk as input. And I want to basically be able to output f of Z1 through Zk with probability at least, let's say, half plus epsilon. That's what I want to do. Okay. So there is some type mismatch happening. C is something that works on just I bits. And this I could be anything. This I could be 1, this I could be n. I mean, you don't know which bit it's managing to predict. Whereas D is something that just takes k bits and is supposed to compute this thing. So we need to set up the stage correctly. So so for now, let's forget about D and let's look at what is the Nisan-Wigderson generator really doing. Okay, so it starts off, it picks up this Y, which I will call, let's say, Y1 through YL. So this is the original seed. And then there's a whole bunch of windows that it seems to create. So this is like Y restricted to S1. And this is Y restricted to S2, blah, blah, blah. And maybe one of these things is, maybe the previous thing is like Y restricted to Si minus 1. And this is like Y restricted to Si. Okay. Now, each of these bits are some specific bits here. Like it just took some of these bits and then that's what is moved in these places. And what is C given? So if I apply F on each of them. Okay. So C somehow apparently takes all of these inputs and manages to somehow output this with high probability. Whatever, with some probability, whatever. That's the behavior of C. Now I need to build D. So D has some input Z1 through Zk. I need to figure out how am I going to use C. So this entire process seems to involve taking some specific Y's and doing something on top of it. Whereas Z only has K bits as input. So if I want to somehow engineer that into it, I need to somehow, I don't know, induce those K bits somewhere inside. So the most natural choice to put those K bits seem to be to put it here. Because that's what you're finally managing to predict anyway. Let's imagine that we are going to set things up in such a way that the Y restricted to Si turns out to be Z1 through Z. Okay. But that will mean that maybe, I don't know, maybe this is now going to be Z1, this is going to be Z2, and maybe this is equal to Zk. But the Y's had L bits in this. It didn't just have K bits. So there's a whole bunch of other bits which don't seem to be related to this at all. So what we are going to do, we're going to, instead of building a circuit, we will now build a randomized procedure. And eventually we will say that, oh, if we can do a randomized procedure, freeze randomness and all is fine. So what we are now going to do is like, in order to run this template, it feels like of the L bits I need to start off with, I know what K are supposed to be. I just don't know what the rest are. Okay, so we just choose them at random.
In retrospect, this was very natural.
Yeah. I mean, it's like, it's not. So this is what we do. So what the procedure D does is the following. Set Y such that Y restricted. Oh, okay, maybe I should first start off by saying the input that we have here is actually Z1 through Zk. Now, based on that, we are trying to say what is this procedure going to do. Okay, so I don't know what's happening to my handwriting. So I'm going to say set Y such that Y restricted to Si, this is actually equal to Z1 through Zk. Every other bit is sampled uniformly. Yes. Okay. Okay, good. Now I want to somehow give C something. I need to give C I minus 1 bits and ask C, what does C think the value of f of z is going to be? Okay. Now the question is, what do I need to give C? So I need to give, the first bit I need to give C is actually C of y restricted to S1. But I don't know what y restricted to S1 is. Because it could be the case that, some of these bits were whatever. I mean, so which means what am I saying? So basically, if I look at y restricted to S1, some of them are like one of these other y's, but maybe a few of them are like blue bits. Okay, and similarly, y restricted to S2, maybe some of them are these blue bits, and these are some blue bits, etc., etc. Okay, even if I imagine all the other y's were chosen with a specific value, like the blue bits that's the input that was given to me. I don't have freedom on that. The other one, I managed to choose things randomly or whatever. But for the moment, let's imagine fixing them to something. This f, nevertheless, it is still f computed. I mean, it's a function f that you are computing on some of them which are frozen and some of them which are not frozen. And like I can't just compute f by myself and give it to C, because the whole point is that I'm trying to say this new circuit is small. And if I'm believing f is hard, I mean, I can't build computations of f within it. Okay, so I need to be a little careful. So the property that we haven't yet used so far about the design is that the pairwise intersections are actually small. So what does that tell us? It tells us that if I focus on, let's say, just this part, the number of blue bits that show up there is at most A. Right? Because the intersection size I know between Si and S1 is at most A. So I don't know what this function is. So I'm just going to define Gi from whatever, Z1 through Zk to 0, 1. And this Gi is defined as follows. So Gi of Z is actually equal to whatever, f of, Gi of, maybe I have frozen these other bits y according to some values. Okay, so I'm doing a bad job about it. So basically what I want to say is, imagine one freezing of all of the other bits. Like everything other than the z's were chosen to some specific value. Now, as I keep changing the z's, what happens to this function? It's some specific function that only depends on a of the bits in the z's that were there. So it's some Boolean function on a of the coordinates that happen to be in that intersection. So every Boolean function has a stupid circuit of size 2 to the a. Okay, because I can just say, okay, accept this input, don't accept this input, accept this input, blah, 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 blah. You just explicitly write down what all you want to accept. Okay, so basically, if I define, that is, this is what I wanted to say, that is Gi of Z1 through Zk is actually equal to f of y restricted to S, okay, maybe I shouldn't call it Gi, Gj. Okay, and by y, what I mean is this. that is build the y that you got from the z's, but everything else frozen to some specific value. Whatever this function is, it's a function that depends on just a bits. Okay, so therefore, these have a silly circuit of size at most 2 power n. Okay, so therefore, now here is the circuit D that I'm going to build. Okay, so I start off with Z1 through Zk. Now what I do is I now build a circuit for G1 based on these. Now that circuit is only of size 2 power. Then I take the circuit G2 based on these. Blah 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 till whatever Gi minus 1 based on these. Okay. Each of these outputs is now supposed to be f of y restricted to S1, f of y restricted to S2, not f of y restricted to Sn minus 1. And this is exactly what C is expecting as input. So put the circuit C on top. Okay, that is going to be my new circuit D. Now there's a whole bunch of things that D doesn't know. D doesn't know what it's supposed to freeze the other coordinates to. And D doesn't really know what the circuits for G1 through Gi minus 1, etc. are. But you know that there is some freezing that works. And there are some circuits of size at most 2 power a that works. So this tells you that there is some circuit of size. What is the total size of D now? The size of D is at most whatever was the size of C. Did I give it a letter for it? I called it S, small s. Okay. So it's at most small s plus something like I minus 1 times 2 power a. That's the new size. Okay. The largest that I would have been is n. Okay. So I might as well write this as this is at most s plus n times 2 power a. And just by construction, you now have the property that if C manages to next bit predict efficiently, it should have predicted the next bit. But fortunately, the next bit is precisely f of Z1 through Zk. So it must have done that with probability half. Okay, so now we can fill in this blank, and this is just going to be S plus n times 2 power a.
So what is constant there? I assume
Sorry, which one?
we just
Now I was just saying that because C is predicting the next bit, like the next bit it is supposed to predict is in fact exactly f of y restricted to Si.
Yeah.
And that is exactly f of Z1 through Zk.
Yeah.
So therefore, whatever C is supposed to predict is what D wanted to compute anyway.
So, where did you use that we sampled y randomly?
So in the sense that I'm just going to say that if I sampled y randomly, then C is guaranteed to predict it with probability half plus epsilon.
And now fix this.
Fix a particular other bit such that this property continues to hold.
Yeah.
And then, yeah, so that's where I use the fact that one. Okay, so this is the proof of Nisan-Wigderson. In hindsight, it's really simple, but yeah, but it just took.
This idea, the Nisan-Wigderson idea, I don't know, but it pervades all of computer science. This idea of that's the Ramprasad theory. What can we do? I mean, in retrospect, always good. I mean, when I first heard, it was completely zapped. What can we do? That this will work. The audacity to think that this will work is what is just pretty amazing.
Yeah.
I mean, the first time.
But for those who work in algebraic complexity, exactly the same thing also works in the algebraic thing, except you need to use one additional property of Kalko. Yeah, just same idea. Yeah. There's but something that you want, on that you put the input you care about, you decide to resample the rest and then just work out what happens. Yeah. Okay. So what is the corollary for this? So the corollary for the above theorem is the following. Suppose someone told you that the function f was epsilon hard for size t. Then you know that the Nisan-Wigderson generator is going to be epsilon by n pseudorandom for size a little smaller than t. okay, which is like t prime, which is like t minus n 2 pi. I'm just replacing them in a slightly different.
And this like here A and L is
Yeah, it is.
same and they are all again, right?
So A and L are like okay. The next thing that we are going to do is like, for example, if you set up a Nisan-Wigderson, if you use the Nisan-Wigderson design that had a specific L and a specific A, then this will show up. So we'll sort of work out some specific examples. Okay. So I was a little sloppy earlier and all. Whenever you talk about a hard function, you're not talking about a hard function really. You're talking about a hard family. Like you have a sequence of functions, one for every length, and each function has the minimum circuit size required for whatever property that happens. And you're looking at that also as when you say that something requires exponential size, what you mean is this growth as the k. So now let's truly get to the right definition of Nisan-Wigderson, which is, let's assume that we are given a family of functions which is 1 over sk hard for size sk. So the epsilon also has to vary, but because I will need epsilon to go down to absorb the factor of n, this is just a small thing that I'm doing, which is that I'm assuming that the epsilon that I'm thinking about is 1 by the circuit size. Okay. And in fact, if you want to think of a concrete example of this, just think of s of k as being 2 to the k by 1000 or something. That is, you're given some function on k bits, and someone is telling you that no circuit of size 2 power k by 1000 can really even guess this with advantage more than 1 by that. That's what is given to you. Okay. So now I want to know how are we going to set up parameters. Okay, so here is how I'm going to set things up. I'm just going, so in order to build a generator, the number of sets, I have to use the lemma that we mentioned earlier. Where was that lemma? This lemma. In fact, it's not 2 to the omega, in fact, it's 2 to the a. Which happens to be, I mean, in most cases, it's like 2 to the omega k and so on. But the number of sets is actually 2 to the a. Okay, so that's the lemma that I'm going to use. So I need n bits to come up with a generator. So therefore, it sort of forces me to choose a to be equal to log n. Okay, and now we need to decide what is my k going to be. Like, if I want to come up with something that stretches something to n bits, I can start with any k of my choice. I need to figure out which of these hard functions do I start off with. So I'm going to start off with a function that is suitable to full, I don't know, size n squared circuits or something. Okay, so what I'm going to do is I'm going to take k to be S inverse of, let's say, n cube. Okay, again, let's put things in context. So if S of k is 2 to the k by 1000, what is the inverse function? It's just 1000 times log n. Okay, so S inverse of k in that case, this is equal to 1000 times log of n cube, which is just 3000 log n. Okay, if S was that function, this is what k will turn out to be. Okay, and now what is L? So this L was basically, what was this? Those 2k squared over a or something, right? That's what my L was going to be. So k in this case, so it will basically be essentially S inverse. I mean, let's imagine it's like k squared. Okay, I mean in the specific example that we spoke about, this is actually going to again be whatever order log n. Because the numerator is some constant times log n the whole square, and the denominator shaves off 1 log n. Okay, this is the setup that is going to be there. Now let's ask ourselves, well, what do we have in the hypothesis? So suppose someone told us that, I mean, by the hypothesis, Fk is supposed to be epsilon hard for size S of k. That was the definition based on the hardness. But we set it up such that what is S of k now? It's just n cube. Okay, so we set it up such that t is like n cube. Okay, good. Now, what does the Nisan-Wigderson theorem tell us? This theorem tells us that if that were the case, then the Nisan-Wigderson generator applied with Fk will be epsilon n pseudorandom. But for what size? The size will now have to decrease by a times 2 power. In fact, I should have written it as it will decrease by what? N times 2 power a. But a was like log n. So 2 power a is another n. Okay, so that is going to be like n squared. Okay. And I know that t was equal to n cube. So which means it continues to be pseudorandom for circuits of size n, but something like n cube minus n squared, which is certainly bigger than n squared. So this tells you that if that is the sort of hard function you started off with, then by going through this process, you now build a generator that now is managing to fool size n squared circuits. This is what we wanted for BPP related stuff. We were dealing with size n squared. So it's just that you tailor your parameters accordingly so that you get the conclusion you want. All right. So, okay, now this just tells us what you are now fooling. But now the important thing is like eventually when you get a generator, the way you de-randomize it, you run over all possible seeds now. But the seed length is now L. And what is L? L was like 2k squared over A or something. So that's what L is, which now is going to be something like S inverse of n cube, the whole square by log. So to get a sense of things, let's just try out various values of S of k and see what do we get eventually. If I eventually want to fool size n squared circuits, what seed length do I end up getting? Okay, so if S of k happens to be exponential, that is like 2 to the k by c, like we were setting c to be 1000 or something like that. So then S inverse is going to be like order log n. So therefore the right hand side is going to become something like order log n the whole square by a log n. So therefore here the seed length is going to be like order log n, where somehow that c will show up in the construct.
Why are we just trying to lay aside n square circuits?
Because if you are dealing with BPP algorithm, let's say running in time n to the c, I can always pretend that it had n to the c inputs and just that it didn't use most of the other inputs and so on. So the circuit size in terms of the new input size is at most quadratic. So that was why we were doing this. Otherwise, you can put that c also as a part of this and nothing will really change. Okay, so if S of k was growing as fast as exponential, then you know that the seed length that you get is actually like logarithmic. This is like the dream scenario. Okay, now suppose S of k was like 2 to the k to the delta, where delta is, let's say, I don't know, 0.1 or something. Then what is S inverse of k? So if delta was 0.1, what would S inverse be?
Log into the
power 10, right? Like log into the power 1 over delta. No. So S inverse of that cube or whatever is not going to make that much of a difference. So there is a square on top of it. So what you will end up getting here is order of log n to the power, I don't know, maybe 2 over delta or something. Okay, so that's what you will end up with. Maybe you will shave off another factor of log n because of the denominator. But if delta is a small constant, this will now become quasi-polynomial. Or this will become polylog. So the running time, if you de-randomize it, will become quasi-polynomial. Okay, and then finally, suppose it was the case that the circuit size was growing faster than every polynomial. Then S inverse is going to be like sublinear, like not just sublinear, it's going to be of the form n to the little o of 1. Right? Because if this was n power 1000, then S inverse is n power 1 over 1000. But you are saying this is bigger than n power k for every k, which means that is smaller than n power delta for every delta. So what you end up getting here is like you get a seed length which looks like n to the little o 1. Which if you de-randomize now looks like sub-exponential time. And this now finally completes Nisan-Wigderson theorem. It basically tells you that if you give me a family that is hard enough, depending on what hardness you are able to provide, I will give you a pseudo-random generator. In the best case scenario here is like if your family is hard in the sense that it's exponentially hard, it's like 2 to the delta k for some delta, then the pseudo-random generator actually gives you, it only has seed length order logarithmic in it. Okay, so all that is okay. And finally, one last point, which we didn't really speak about much, is that eventually when you want to use this for de-randomization, you want these generators to also be able to, you need to be able to compute these generators quickly. Now, finding a design is easy because we said that there are explicit designs. But as a part of this Nisan-Wigderson generator, you not just need to find a design, you also need to evaluate f on those points. Okay, so it will turn out that as long as you assume that this f is computable in exponential time, maybe you take 2 to the 1000k to compute it. Okay, that will then tell you that the generator is also computable in 2 to the order k time because computing the design is like barely anything. Now, this tells you some upper bound for computing f. So you now have a truly explicit generator. All right. So that finally completes the Nisan-Wigderson proof, which says that suppose you have a family of hard functions, which is in E, that is, this family is actually exponential time computable, and you are given that it is at least this hard. Okay, then you can de-randomize BPP in time, which is like 2 to the order S inverse of n cube. Sorry, did I miss a square? Whatever, it's like S inverse of n cube, the whole square divided by log n. Yeah.
So I just wanted to go over where did we use that for pulling SK type things? The error threshold needed to be 1 by SK.
Oh, so I'm always going to, okay, I should have actually, good point. I should have mentioned, it says that I want to absorb this extra factor of n. So I'm going to be dealing with, I need to work with it. I want to be able to fool like I need to work with an epsilon that looks like 1 over n or something. So that's why I need I mean, if everything is just 0.1 fooling, for large n, I don't have anything that is like 1 over n fooling. So I'll have to work with a large enough thing so that it drops below 1 over n. From that point onwards, this works. So that's the one annoying catch.
And S of k is sort of comparable to n.
Yeah, S of k is like comparable to n. So because you are always expecting.
Yeah.
Okay, so that completes the Nisan-Wigderson proof. So in the rest of the time that I have, what I'm planning to do is actually to give you an outline of how you can hope to strengthen the result. But we won't be able to do a lot in terms of the proof here, but hopefully we'll start bringing in connections as to what exactly do we need in order to strengthen this result. And by strengthening this result, it's just going to do the following. It's just going to weaken the hypothesis. At the moment, the Nisan-Wigderson theorem. Again, let's imagine that the only thing I care about is showing that BPP equals P. Okay. And for that, I want some function which is 2 to the delta n hard. That's my goal. I mean, it should be 2 to the delta n hard to guess. Okay. Rather than asking for a function that is 2 to the delta n hard to guess, can I ask for a simpler function, but somehow still get the same conclusion? So that's what we are going to try and do. Okay. So to strengthen the result, we are again going to be someone gives us a family fk, which is in exponential time. But the question is, what am I expecting out of fk? What do I want from fk? So the current hypothesis is that fk is epsilon hard to guess. Okay, by some size sk circuits. Again, think of sk as 2 to the delta k. That's what sk looks like. And to write it differently, this is a statement of the following type. It's just saying that for every circuit C of the appropriate size, you have this property where this property is over the choice of X. Okay, if you want, you can say C is a randomized circuit or whatever and deal with this. Okay. Now, I'm going to define one weaker hypothesis now. Okay. And the current hypothesis sort of says that I want the function, I want no circuit to be able to do anything significantly better than guessing, like randomly guessing. But maybe that is too hard. Okay. So the hypothesis is going to be that I'm going to say that a certain function, that same family f, is epsilon hard to approximate by size S of k circuits to really mean the following. That the probability that you actually equal f of x is at most half minus epsilon. Sorry, 1 minus epsilon. Okay. And in words, this is like saying that no matter what small circuit you take, it must make a mistake on epsilon fraction of the inputs. There's no circuit that must be able to get really good close to state. So this current hypothesis is actually here where epsilon is set to something like half minus a little bit. You're asking for every circuit to make a mistake on 49% of the inputs or something. But maybe you don't care about it. Maybe suppose I give you a function with only the guarantee that every circuit makes a mistake on, I don't know, 1% of the strings. Well, is this something that you can work with? Can you? Yeah. And here is weaker hypothesis 2, which is the extreme version of this, which is that all I want is that this function cannot be computed by circuits of this much size. By which what I mean is that for every circuit of small size that you pick up, there is at least one input on which you are wrong. Okay, and this is called a worst case hardness assumption. Okay, and we would like to know that no, at the moment I know I can get the Nisan-Wigderson conclusion if I assume this. Now, what I want to know is, can I get the same conclusion if I assume this, for instance? Or can I get the same conclusion if I assume this? Okay, so those are the sort of statements that we are going to try and move towards. And so the question that we are basically asking is, can we work with this, whatever the weaker hypothesis that we managed to come up with now, and get the same conclusion? Like suppose I just know that I have something computable in exponential time, but my only guarantee is that like every circuit of size 2 to the k by 1000 will make a mistake at least on one input. Is that sufficient for me to say P equals BPP? Okay, and basically Nisan-Wigderson showed that the answer to this is yes. Actually, you can get the same conclusion of Nisan and Wigderson from just the weaker hypothesis too. And this is the theorem that basically says that suppose you know that exponential time is not a subset of size 2 to the delta n. That is just a rephrasal of saying there is something in exponential time which cannot be computed by circuits of size 2 to the delta n. Then P equals BPP. Well, why? Because it somehow says that using that function, whatever that function is, I am able to build a generator which will then manage to fool blah blah blah. Okay, so that's what the Nisan-Wigderson theorem states. And this is what we are going to try and prove in the next maybe 3 lectures or something like that. So is the statement of the theorem here?
You need to somehow explicit function which
so that
is E and not in
it's
right?
I mean, but the explicit function is because it is in E, right? I mean, like, so I'm saying there exists a function there that happened. I mean, that satisfies this property.
But so like for this assumption, you cannot use like a computation argument to prove that such function exists, or
Sorry, which
like the assumption is this there is some delta such that this
yeah,
then P equals BPP.
yeah.
Right, so just by counting argument.
So the counting argument will only tell you that there exist functions which maybe have circuits of size, let's say 2 to the 2 delta n, which are not computable by circuits of size 2 to the delta n. So it will give you non-uniform functions which don't have this much circuit size.
So
the thing is, what we don't have is like a uniform thing, something in exponential time which has this property.
I see. So the counting argument cannot.
Yeah, unfortunately, the counting argument doesn't work when you're dealing with the lower bound of this type. Okay, but the point is, I mean, like this is the reason why complexity theorists generally believe that P must be equal to BPP, because it just feels very weird if every damn language in exponential time happens to have a circuit that is smaller than 2 to the delta k for every choice of delta. Okay, maybe we don't know how to prove it right now, but it seems
non-uniformity is a dramatic.
yeah, unless the fact that you go from algorithms to circuits somehow dramatically increases the power of computation. It somehow feels like this cannot be true. I mean, yes, it is true that circuits of small size can do things that algorithms can't do. But that's not what we are saying. We are saying that, is it possible that everything that's actually a legitimate algorithm, somehow when you phrase it in a circuit language, it's like dramatically smaller. And it feels like that ought to not be the case. And this is like saying that, well, if you believe that statement, you should believe that, like, as far as decision problems are concerned, randomness doesn't give you any power. You can always be random.
Except if you are charting.
No comment.
Charting believe that.
Oh, believe that.
I mean.
Oh, I see. Okay. Yeah, but this is one of the reasons why people will say that, whenever you see BPP or something, you're like, oh, basically it's P, it's just that we don't know it yet. Okay. Okay, so here is how the roadmap is going to proceed as to how the proof is going to be done. Except, I will tell you the roadmap which is the most natural, but we will sort of short circuit this roadmap a little bit. Okay, that's what will happen. But here is typically how it is. You start off with the assumption that someone gave you a function which was worst case hard. Like in the sense that you are guaranteed that every circuit makes a mistake somewhere. Now from this, what I'm going to do is I'm going to use this function to build a different function. Okay? With the property, which is now, it's not going to be on k inputs, it's going to be on some k prime inputs. Okay? But now you have the property that if the original function was hard to compute, this new function is actually hard to approximate, in the sense that every small circuit will actually not just make a mistake once, it will make a mistake on constant fraction of inputs. Okay, that's going to be the first step of the process. So we're getting closer there, but of course 1/50 is not going to be good enough to now plug Nisan-Wigderson. I need to get half minus epsilon. Okay. And now the next step is going to be, we're going to do one more such thing to now come up with a different function, which is now maybe on 0, 1 to the k prime at this point, such that this new function is actually hard to guess. In the sense that no small circuit can even get like bigger than half plus epsilon. Actually, the epsilon, that epsilon is not 1/50. So this epsilon is like whatever you eventually need to then plug in to the Nisan-Wigderson generator. So this is roughly what the roadmap of Wigderson theorem is going to be. You're going to start with the assumption that somebody gave you an f. These are things that you can build yourself. You will know, given an f, how to get f tilde and f double tilde. And f double tilde is what is fed to the Nisan-Wigderson theorem to get the conclusion that you eventually want. Now, obviously, these transformations need to therefore satisfy some properties. I mean, you'll have to do something with respect to these transformations. So in today, what I'm trying to get across is like, what are some candidates for these transformations and what are the important properties? Like, for example, at this point, it feels like, how is k prime supposed to be related to k? Like, what should I be like hoping for? And so those are questions that we will ask. And the other thing also is like, f was told that, f was somehow efficient in the sense that it was exponential time computable. There's some upper bound that we had. Well, if I had such an upper bound, I would write an upper bound for f tilde and f double tilde. Because eventually when I plug that into Nisan-Wigderson theorem will expect that this is exponential time computable. So there's some properties of f need to carry over. We need to figure out exactly what are the relevant properties and how should they map when you make these transformations.
So and how does it eventually show the way right now our hypothesis is exponential time has some problem that is but if we only had weaker hypothesis that
so the same thing it will translate appropriately.
So it will, instead of p being equal to BPP,
you will have that p is like sub-exponential, but it won't just be s inverse of k whole squared sort of a thing, because every single thing will degrade it somehow.
Okay.
But I mean, like if one goes through the thing, you will get something non-trivial. Okay.
To get, so right now, the best hypothesis we know to get E is equal to BPP is that E is not in.
More or less, I think, yeah. Maybe there are, I mean, there are some subsequent results that says like de-randomization under uniform assumptions and stuff like that. But morally speaking, this is the best that we know of. Whatever the weakest hypothesis that seems to imply B. Okay. Now that I've said that, we'll eventually sort of see that there will actually be a one-shot transformation from that to here. Okay. And so the previous arc that I was talking about is what Nisan-Wigderson actually did in their paper. Okay. And the subsequent thing was actually done by Madhusudan, Luca Travesan, and Salivatan, which is the proof we'll actually be following. But I will still try to do many of these other steps because even though this is a one-shot transformation, the ideas that go into it were all present. I mean, like just presenting the main crux here will just feel like, pulling a rabbit out of a hat. So we will still go through each of the processes, but I'm just telling you that there is a one-shot way of doing it. Okay. So here is what we are going to try and do. Okay. So let's try to focus on just step one. What do I want? I'm given something. I'm given a certain function with some worst case hardness guarantee. And from that, I want to get a function which has some sort of average case hardness guarantee. Okay. So let's just write down what we want. That if f is worst case hard, or let me explicitly write down, if f is such that every circuit makes at least one mistake, then I want f tilde to have the property. I want this to imply this. F tilde is such that every circuit, again, by every circuit, I mean every circuit of small size, blah, 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 makes, I don't know, 1/50 fraction of mistakes. Okay. So this is what we want. So now let's just look at the contrapositive of this. What's the contrapositive of this? I'm going to replace this arrow the other direction and negate both the statements. So what is the negation of the first statement? Every circuit makes at least one mistake. The negation is that f is computable by a small circuit. Okay. So what is the negation of the second statement? So previously we were saying that every circuit must make a mistake on at least 1/50 fraction of places. But what is this going to be? This is like saying that f is approximable by a small circuit. That is what I mean by this, is that there is some circuit that happens to compute f tilde on 1/50 fraction of places. Okay, but everywhere else it's maybe doing something crazy. But somehow from that, I want to be able to build a different circuit for f that computes f exactly. Okay, so what does this smell like? You want to say if something can be computed at a good number of places, I want to be able to come up with something else which gets it right everywhere.
Yeah.
And this is exactly error correcting codes, right? So it somehow sort of says that if f tilde was like the encoded version of f, well, if you can get f tilde right at a lot of places, you should then be able to decode to get what f is. Okay, and this is exactly error correcting. Okay, so what we are going to do is we're just going to define f tilde to be some error correcting code applied on f. What do I mean by applied on F? Well, basically think of them as truth tables. So by F, I mean just imagine the string as being the large truth table. Apply the error correcting code on F, you will now get a larger string. Interpret that larger string as a function and call that F filter. Okay, so that's what the transformation is going to be. And what we want is basically that if someone gave you a circuit C tilde that apparently approximates F tilde, if I think of C tilde as truth table, well, that's the same thing as saying C tilde as truth table and the actual F's truth table. Okay, F tilde as truth table, they agree on some delta fraction of the places. So hopefully you can then decode from that to get the actual message, and which in this case the message was basically F. Okay, so you can just decode from that. And so basically that's what we are going to do. It's just that we need to be a little careful about what do we mean by decode. Okay, so let's ask ourselves, how are we, okay, what is it that we are trying to get here and what does typically decoding mean in the error correcting part? Okay, what do I want? So standard decoding. Okay, so I have the circuit C tilde, which I have now expanded out as a truth table. And apparently, this is like, this agrees with the truth table of F tilde, which is the encoded version of F. In the sense that there are lots of points in which they are the same. There's some delta fraction on which it's the same or whatever. Okay. And the actual F is the message that I care about. Typically, what you have is that if you tell me what this is, I will run in polynomial time and tell you what this is. That's how typically error correcting codes work. But notice these strings are just way too large. Like, what are we eventually going to argue? We're going to say that if someone gave me a small circuit that happens to do this, that has that truth table, I want to build a small circuit that computes F. If I say the overhead on top of C tilde that I'm going to put in order to decode requires the truth table length of C tilde, well, that is going to be way too large, because even if C tilde works on a small number of bits, I'm now going to end up running an exponential in that much time just to read the damn truth table. And that's something that I can't afford to do. Okay, so now let's ask ourselves, what do we really want? So when we say I want to compute F or to compute F exactly, etc., I am given a specific input X. Okay, so what we want is that we are given a specific input X, which is like one coordinate in the message. Okay, I don't really care about the entire truth table of F at all. I just want to know in the corrected message, what does that bit correspond to? So in that regard, it's feasible that maybe you don't need to read all of C tilde at all. Maybe in order to figure out this X, you maybe read just this bit, this bit, this bit, and this bit or something, do some specific computation on top of it, and then say, oh, the corrected message, the value is actually F or something. So you would want a decoding procedure which is not even looking at the whole input, as long as you only care about a specific bit of the message. Okay, so this sort of moves us to this definition, which is called a local decoder. Okay, what is a local decoder? And let's say you have an error correcting code that maybe maps strings of length capital K. Notice that capital K is true to the small k, because if you have a function on small k bits, the truth table is of length capital K. So that's why I use this. So just imagine that you have some error correcting code that took messages of length capital K and mapped them to messages of length capital K time. Okay, we will say that this admits a delta local decoder. A local decoder is just some randomized decoding procedure which has the following guarantee. Okay, for every specific point X that you care about, that X is this, whatever, that location you care about, and somebody gave you a received word, which is D. So basically the truth table of the circuit C prime is playing the role of G. Okay. And you're given the promise that G is like actually delta close to an actual encoding. There is an actual encoding F and like it is delta close to that encoding. Then I want this decoder to be able to return the value at X with high probability. Except the decoder is not going to run in time proportional to the length of G, but it sort of has read access to G. Like any specific bit of G it wants, it can go and query that. So that's why I put G in the exponent to sort of mean like it's like it has oracle access to G. Okay. And typically, we would want the decoder to run in polylogarithmic time. Like I don't even have time to read the entirety of the truth table of G. Okay. So this is what I would want. So this is the definition of what is called a delta decoder. And we will say that a code is delta decodable if there exists a decoder with small decoding whatever. Okay. So now here is a simple lemma which sort of like it helps us set our goals, which is suppose someone told us that there is some error correcting code, which is some explicit error correcting code, blah blah blah, which happens to have a delta decoder. Okay. And let's assume that the delta decoder runs in time, I don't know, T decoding, the time taken for decoding, something. Okay. Now I want to say that suppose someone gave you a worst case hard function. You took the truth table, applied the error correcting code on it, interpreted that as a function F tilde. I want to claim this new function is now delta hard to approximate. Okay. So that's what. Did I mix up delta and 1 minus delta? Anyway, we'll see the proof, basically what happens here. And the proof is like sort of fairly simple. So what are you going to do? So you're just going to run so I want to build a circuit, whatever, D on input X in K. Okay, that's the input that's given to me. I need to come up with a way of guessing what f of x is going to be. I want to actually compute f of x with high probability. Okay, so what am I going to do? So on input x, so here is what I will do. So I'll basically run the decoder given this circuit. Sorry, I should be doing it here. Okay, let me just state it the following way. So I am told that f tilde is approximated by a size T circuit. Let's say that circuit is C. Okay. Now I want to build a different circuit D that computes f correctly. But again, I'm going to build a randomized process for it instead. Okay. So now how am I going to build a circuit for D? So the circuit D is as follows. So the input is some x. Yeah. Okay, so what is D going to do? So it's just going to run the decoder with whatever this oracle access to the circuit C and on input X. Okay, and basically just return whatever this returns. So of running, I should just say return. Okay. Now let's look at the running time that this algorithm takes, or whatever is the circuit complexity of this. Now this decoder just by itself will take T decoding many times. Like whatever T dec, that's the total, that's the running time of the decoder. So which means it's going to make at most T dec many queries to C. But every time it makes a query to C, I actually need to do that computation. Right? I'm given C, which is a size T circuit. So I need to evaluate T on that particular size T on that input and see, okay, what is the value? So the total running time of this process is like roughly T times T dec. I said everything in terms of an algorithm, but you can convert this to a circuit and so on. So this tells us that if someone told you that there was a circuit to approximate f tilde, the definition of local decoding says that this must actually compute f correctly. Okay, so that's it. So this basically is going to tell you that if we can find an error correcting code of this property, that it has a local decoding procedure, etc. This immediately is going to tell us that I can go from like worst case hard to some average case hard, depending on whatever this local decoder works for, like the threshold that that thing is going to work.
Okay. Again, we treat the randomness.
Yeah. So all that we'll do. Okay. Now good. So therefore, the goal is now going to be the following. We can just ignore all of everything that we are doing with respect to hardness, etc., and just focus on local decoder with a bunch of properties. I'll just try to give a sense of why do we need each of these properties. So the first thing is I want the local decoder to be computed in poly k time. Well, the reason is because I'm going to start off with a circuit and come up with a different, start off with one function, come up with a different function. I obviously want this procedure to be efficient as well, because the final generator is going to depend on this. Because the final generator running time will be like, I start off with f, I somehow transform it. Now, I don't want this transformation overhead itself to be massive. So that sort of tells you that the first thing should come. So the first thing also implies that the second thing should happen. Because if the encoding procedure only takes poly time, then of course the length can only increase polynomially. Okay. Notice that this immediately implies that this small k prime is just a constant factor of whatever was this old k. That is, if you have a function that depends on, I don't know, k bits or something, the new function f tilde now it depends maybe on, I don't know, 100 k bits. Okay, so that is one. And secondly, I wanted to have a delta decoder which is super efficient. Because the worse that efficiency is, I'm going to take a hit on what sort of circuit sizes I can tolerate. Because if I know that f was hard to compute by some size, the moment I go to hard to approximate, I will lose out a factor of TD, whatever, this TDEC in that thing. Right? So therefore, I need to make sure that this TDEC is not something that is going to hurt me a lot. And hopefully, as long as it's some poly k or something, that is something we can tolerate. Sorry, polylog capital K, which is like poly in small k.
So here, right now, all of this is small k, right?
No. These are capital Ks. Because the error correcting code is encoding a truth table of a function on small k bits to some other string.
Yeah.
So the truth table of a function on small k bits is a string of length capital K. Okay, and
ECG computable in poly, that is
poly in capital K. This is poly in capital K because I need to output the entire truth table. Okay.
Wait again, what did we? So in the end, when we are trying to correct this, we want to be able to look at only a few of the things in this truth table. So,
right. So that's where that is coming. So we basically want to say that if I am dealing with a size, I don't know, size T circuit that apparently approximates this f tilde, what is the circuit that actually computes it? Well, you do the same thing, but now you use the decoder. But the decoder is going to incur a cost of TDEC. And I want to make sure that this TDEC cost is not much. Right? So that's what this is. So basically, so therefore, what is left right now is to get a sense of, firstly, do we have these local decoders? I mean, are we just building castles in air? Well, do these objects exist at all? So in the remaining about 15 minutes, I'm going to give you a code that you have seen so far, which actually has a local decoder. This code will not be good enough for the above purpose, but nevertheless, it will set the stage for things that are going to happen in the next couple of lectures. Okay. And I'm going to give you one explicit example. And this example is again going back to the Hardness code. Okay. Recall that what is the Hardness code? It's something that takes a string of length k and returns a string of length 2 to the k. Okay, and how should I interpret the string? If I think of this as x, so this is going to be v inner product with x as v ranges over every single vector in f2 to the k. Okay, that's what the Hadamard code is. Now, obviously, this doesn't satisfy the above requirements because this thing is certainly not poly-k. It's like making the truth table really, really large. Okay, those are things that we will have to figure out. But I want to claim that this actually is locally decoded. Okay. Now, so the theorem is that Hadamard. Notice that, by the way, firstly, we saw this last time because the distance of the Hadamard code is actually half. So even if you forget locality, if you want to do decoding, the best you can hope for is like a delta being like a quarter, because it has to be half the minimum distance, right? To be able to exactly figure out what is the code word that is within delta. Forget even doing it locally. Okay, so I need like a quarter is the best I can hope for. I want to say Hadamard has a local decoder, whatever, delta local decoder for any delta that actually looks like a quarter minus epsilon. Okay. And so here is a proof of this. I'm going to state it differently. So there is a hidden input X. Okay. We don't know what message was encoded. And I'm trying to figure out the ith bit of the message. I want the ith bit. Let me, without loss of generality, say I want the first bit of the message. That's what I'm trying to compute. What I'm given is this long string z1 through z2 to the n, or let me, I'm going to call this as zu1 through zu2 to the n, where basically each ui is a vector. Maybe I'll just call it v. So I'm given zv, which is supposed to be equal to the inner product of v and x. Maybe let's not say this. Okay. So zv for all v in f2 to the k. So that's what is given to me. But if this were the Hadamard encoding of x, now obviously one of the things that show up is x inner product with e1, the indicator vector which just has 1. So I will just read it off that. But obviously I am not given this, which is the Hadamard encoding. All I know is that the distance of this thing from the Hadamard encoding is at most a quarter minus epsilon. Okay, given this, such that the probability over the choice of v that zv is actually equal to the inner product of x and v, this is at least 3/4 plus epsilon. That's what is given to us. So z is what I have access to. I am interested in computing xi or x1. Okay. Now, okay, what can someone think of a local decoding procedure for this?
Pick random v and with v and v plus.
Exactly. So local decoder with respect to, I don't know, coordinate 1 or something. Okay. What you do is the following: you query z. Okay, maybe I should say pick v at random. Okay, query zv and zv plus e1. Okay, return zv XOR with ZB plus E1.
That's your VLR.
In fact, it's exactly just that. Okay, so now I'm just going to argue that this actually gives you a decoding procedure that has a non-trivial probability of being built. Like, okay, we'll just try to figure out at this point, this decoding procedure, what is the chance that it gets X1 right correctly? Sorry, what is the chance that it gets X1 right? Okay, I want to get that probability. Okay, so probability that decoder with respect to Z on 1, this equals X1. So if two good events happen, we are already going to be in some decent shape. So ZV, if it so happens that ZV was actually equal to X inner product with V. Okay, and if it so happens that ZV plus E1 is also, at most whatever, it's actually equal to inner product with X and V plus E1. Obviously, their XOR is going to be X inner product with E1, which is X1. Okay, so I'm going to say that the probability that this was wrong, I mean, it's certainly no more than the chance that one of those two things happened. Okay, so this is at most the probability that ZV is not equal to X and V1 over the choice of V, plus the probability over the choice of V that ZV plus E1 is not equal to inner product of X and V plus E1. I don't know why that V1 happened. Okay. Now, what's the chance that the first thing happens? So the definition of Z was that as I range over V's, I'm actually equal to inner product of X and V with probability at least 3/4 plus epsilon. So the chance that I am not equal to inner product of X and V is at most a quarter minus epsilon. Okay, so therefore the first quantity is at most 1/4 minus epsilon. Great. What about the second quantity? Now,
So it's the same.
it's the same thing because the point is E1 is a fixed vector. If V is uniform over the entire space, well, V plus E1 is also uniform over the entire space. So it's basically the same thing. Okay, so the second quantity is also at most, quarter plus epsilon. Quarter minus epsilon. Okay, so therefore together, this is at most half minus 2 epsilon. So the chance that you are going to correctly decode is a little better than half. Okay, but then when we define the decoding procedure, we said that no, I want to be able to decode with high probability. No, just half plus epsilon is not good enough for me. I want to get really, much higher probability to get it right. But now it's a simple thing, right? I mean, like, you're going to get it right with probability half plus 2 epsilon. Well, you just try out many attempts and take the majority of all of them. Each time you try something, you're going to be right with probability half plus a little bit. So standard Chernoff bound will now tell you that the chance that the majority of them were wrong was exponentially. So the actual decoder is now going to be try a few and take majority of this big thing. This is what you do, but you try out a few times and then take them. Now, if you work out, now you can notice that every single part of the decoding procedure really just made 2 queries. And if you're doing Chernoff, depending on how much error you want to get or something, maybe there is some log 1 over epsilon or poly 1 over epsilon that will show up, but nevertheless, it's some constant. So this will basically tell you that with high probability, you can actually figure out the correct value of x1 by just making a few queries. I mean, obviously the encoded version is massive. You don't have time to look at all of them, but you're able to probe the thing at various points and then able to figure it out. So great. So this tells you that the Hadamard code is actually, it has some local decoding properties. Okay. And obviously the main issue is that, well, I mean, like you have this great delta and so on, but the point is, this is just not true. I mean, the rate of this code is like absolutely terrible. Okay, and this is not something that you can afford for this procedure. Okay. So you can sort of flip it around and sort of say, okay, let's look at the other case and let's look at Reed-Solomon codes. Now, Reed-Solomon codes, you don't just have unique decoders, you seem to have very good list decoders and so on. It's unclear what list decoder means in the local setting. But somehow it feels like that also has some amazing properties, which ought to be useful. And it has amazing rate. Okay. Well, but somehow it looks like we don't know if it has local properties there. And somehow it feels like if Hadamard code has local properties and Reed-Solomon code has amazing rates, hopefully there are some things in the middle that have decent rates, but also have local decodability properties. Okay, and the codes that are in the middle between Hadamard and Reed-Solomon are the Reed-Muller codes. So that's what we're going to do next time. Okay, we'll start inspecting local decodability in Reed-Muller codes. Okay, and in fact, the final Sudan-Travesan-Vadan theorem was just this. You set up a Reed-Muller code with appropriate properties. You take your worst case hard function, apply the Reed-Muller encoding of this hard function. That turns out to be hard enough to just directly apply Nisan-Wigderson and you get your theorem. So that's the final proof. The argument will now say that if the Reed-Muller code, I mean, in fact, there are going to be lots of things that we have to change. It won't just go via what we have done. So unique decodability will not be good enough because we'll have to get half minus delta. Like in order to apply Nisan-Wigderson, we'll have to get really close to half, and that won't even be half the minimum distance. So unique decoding is impossible. So you need to do list decoding. But now you need to come up with a definition of it. What the hell does list decoding mean in the local setting? And in fact, that was STV's one of the primary contributions. Is they gave a definition of what does it mean to say a code is delta locally list decodable. And it's a very clever definition. And once you have the definition, the next couple of steps is just going to be, we will show that Reed-Muller code is in fact delta locally list decodable. And then it just plugs in and you just get from worst case to average case.
So locally list decodable would just be that you can read a few points and then output then these are the.
So the catch is the following. You're going to output a list of one. So you wanted a specific value. So maybe the answer could be like you output a list of possible values that this can attain. But if you're working over a small alphabet, what is going to say, oh, my list is 0, 1?
Right, earlier, I mean, okay, yeah, makes sense.
Right, so there's something that should prevent you from sort of just saying that you are interested in a specific value. I will say the list is basically the entire alphabet. So that's not helpful. So you need to come up with a different definition whereby you are somehow saying that you're doing something not trivial. Anyway, so that's what we're going to do in the next class. So in the next class, one of the things that I first want to do is complete the unique decodability so that you go from worst case to some average case. We'll just use the delta unique decodability of Reed-Muller codes to get that 1/50 or something. That's going to be the first step. And then we'll have to come up with a definition of locally list decodable codes to eventually go from worst case to directly to whatever, hard to guess sort of case. And yeah, so that's going to be the agenda for the next couple of lectures. Okay, cool. So then let's meet.